Welcome to another Lightblade Learning. Now, in a fairly recent session, I attempted to give you all the knowledge that I had about photo engraving. Now, I've since been able to learn a little bit more and rationalise all that I've learned into a fairly simple set of instructions. Now, there are some calculations in there, but nothing difficult. And what I'm going to do today is to summarise in just this one simple session how to go about producing excellent quality photo engravings. These are basic rules and they will guarantee that you get a good quality product. But you might decide to veer away from those rules and experiment for yourself. That's your choice. I'm only giving you the foundation upon which you can build. Now, to go along with this session, we have a 2-page document here which summarises all the steps that I'm going to demonstrate to you today. So, in conjunction with some of the fiddly details that I'm going to show you on the video, you can go through the basic steps here with this document that will be published on the Thinklaser website. Now, today's session will start right at the beginning and we're going to do every step of the process. But in future, you won't need to carry out every single step of this process, only some of the steps, because once you've gathered the information today, it will be valid for the future. Step number 1 is to choose the lens that you're going to use. Now, the one thing that you will find about doing engraving work is that the nozzle will tend to get sticky around the outside because of the way in which the fumes will come upwards and stick to the outside of the nozzle. So from time to time you'll need to inspect the nozzle and maybe clean it with some acetone. Now, before you do that, you might want to check that you've got a nice clean hole in the end of your nozzle, and you can do that with a 2.5mm drill. Literally, just make sure the nozzle is clear. And then we'll just clean the outside of the nozzle there. Now, the inside does tend to get a bit fogged and messed up, but it's not essential to get in there to clean it, although from time to time I do, just to take the debris off the inside of the nozzle as well. Your Thinklaser machine will be supplied with 3 lenses. It has a 2-inch lens, which, to be honest, is normally a very good quality meniscus lens. Now, when you look in there, you'll see that it's a greeny colour, and if you hold it up to the light, you will not be able to see through the lens, and that's because it's made of a material called gallium arsenide. Now, most lenses that you can get, the cheaper lenses, are made from something called zinc selenide, which work perfectly well. This is a good quality lens, and the meniscus lens helps to focus the light down to a slightly sharper point. So, whatever lens you're using, and I would normally recommend for engraving work that you use a 1.5-inch lens, but sadly, this system does not allow you to use a 1.5-inch lens. A 2-inch lens will be perfectly okay. You'll be able to produce perfectly good results with a 2-inch lens, but you would get slightly better results with a 1.5-inch lens. And if we get time, I have got an adaptation for this system which will allow me to put a 1.5-inch lens in here, and we'll see what the difference in the quality of the pictures are. And I think you'll see that there isn't a huge difference. So step number 1, choose your lens and make sure it's in good working order, clean, and the next thing is to make sure it's correctly focused. Now, I've shown you this photo engraving of one of my old girlfriends on previous occasion. It is almost the perfect formula, but not quite. Now, as I've mentioned before, this binary picture is composed of just dots. There is a white background and dark dots. Now, it looks as though we've got lots of different shades of dots in that picture. Not true. They are literally one colour dot. but it's the mixing of the white background with the different densities of those dark dots that creates this impression of a grayscale. Now that's a very, very important thing to remember. The white background is very important. If you make the dots too big, or you overlap the dots because you try and make the picture too high a resolution, your eye will not be able to sort out a white background. It will just have a series of dark dots. And so the grayscale effect that you're looking for disappears. Today is all about the rules for getting the features of this picture correct. The dots, the size of the dots, the power of the dots, and the resolution of the picture that you start with. Now, with a card, which is what this is, or leather, a natural leather, maybe a piece of MDF, all those sorts of materials, wood, they're all what I call organic materials. They will burn, and they will burn with a brown mark, which is great because brown is quite a dark mark. So we can have a dark dot on a white background, which is exactly what we want to get a good quality picture. Now, when it comes to what I call mineral materials, slate, stone, granite, or plastics like maybe clear acrylic, the situation is different. We do not get black dots. We get a black background or a clear background, in the case of acrylic, but we get white dots. Now that means to say that the picture has to be converted into a negative before you print it. So something else that we're going to talk about along the way. For the purpose of this exercise, I'm going to be using a white card. It's about 1mm thick, and to be honest, I think it's the sort of card, fairly soft card, that you probably would make beer mats of. It's not high quality, but it's nice and soft. So it's actually very good for doing pictures on. And it's not expensive to buy. Now, it is important that you use a piece of the material that you're going to work on to do these settings, because what we're going to do now is find not only the focus, but we're also going to find the size of the dot. And to do that, we need to be working on the correct material, because different materials will produce different size dots. Okay, now my focus gauges are basically, this one is millimeters and this is 0.5 of a millimeter. So for instance, this one runs from, I think, 1 to 20, and this one runs from 1.5 to 20.5, because I've added an extra half a millimeter onto the bottom. So they're very simple gauges to make. And what we're going to do is we're going to lift this up, and we're going to drop it down initially onto the 8mm step. We're going to run my test program. And that's it. That's all the program is. So this is 7.5. Just drop it down onto 7.5. Now I'm going to do a manual inspection on these using this device here. Now this is something called a linen gauge, and it's a very handy device that you will probably need to measure these and to look at these with. Now this is easily available on, you can get it off eBay for about £5, a plastic version, 10 times magnification, which is absolutely super for doing this job. So I've put all the details in my separate write-up. No, for 6, not really for 6.5. 7 looks a lovely clean set of holes or dots. 7.5, not bad, but in general I would think I've got a crisper set of holes at 7, and 8, well, that's not particularly brilliant either. But we'll see those under the microscope and you'll see what I mean. Now this little pattern is very carefully designed to tell you all sorts of things. The first thing it will do, it will enable you to estimate the size of the dot, and I would say that we are looking at dots that are at probably 0.2 diameter, and I'll explain more about that when we see them under the microscope. Now, before I try and describe what we're seeing under the microscope, let's just take a look at the pattern that I laid down as the basis of the test. What we've got here is a set of pixels. These are very carefully sized. Each one of these pixels or spaces on the bottom line is 0.1 of a millimeter. Let's take the bottom line for example. If I see a dot, then a space, then a dot, and the space is the same size as the dot, then I can estimate that I've got 0.1 millimeter dots. Now if the dots touch on that bottom row, then it can only be because the dots are 0.2 diameter. Now we can apply the same principle to the next two rows of dots. So if I get 0.2 dots, there will be a dot, a space, a dot, a space, a dot, a space, and the space between the dots should be the same size as the dots themselves. So that will tell me that I've got 0.2 dots. And then obviously if the dots are touching, then it means those dots are 0.4 diameter. And of course between the 0.2 and the 0.4 we can estimate a 0.3 dot. So I don't expect anybody to be using 0.4 dots, but if you've got your focus badly set, you may well find that you've got 0.4 dots. Now, the purpose of the top line with those dashes on it is nothing to do with sizing the dots. That's all to do with assessing what power we're going to use to do the picture. And that will become obvious as we do the next test later on. Now this bitmap pattern will be available on the Thinklaser website, but you'll have to put your own parameters to it. And what I suggest you do is to run this at fairly low values. First of all, I would set the speed at about 50 millimeters a second. We've talked quite a bit about high frequency impact engraving and how there is this strange pre-ionization zone on your tube before it really kicks in and starts developing power. Most engraving really needs to be done at low power, and this particular zone up to, on most tubes it could be 12, could be 14%. You will need to test your own tube to find out where the limit for that zone is, and I would stay inside that zone if you possibly can, because you will get much better results. On both my machines I can safely say 11 or 12% stays inside that zone, so I'm going to set this to say 12%. We need to make sure that we've got none of this stuff here ticked. We're just going to use standard X swing, but bear in mind what I told you was that the size of these dots is 0.1 millimeters. Therefore that's what we're going to be using for a pitch, 0.1. So let's go and have a look at the results that we got. Right, we're going to check out the test pattern for our 2-inch focal length lens. Now the first thing we did was to set the gap underneath the nozzle to 6 millimeters, and here's what we got. Now our first two lines at the bottom here are, well, they're not really two lines, are they? They're a bit of a blur. You certainly can't see any dots. So let's move to 6.5, and all of a sudden we can see some dots. That's 0.5 millimeter difference in the focus. Makes a significant difference. So let's step up to 7 millimeters. And here we are, we can see definite dots. Now please excuse me, I've got no idea what these funny S-shaped things are here. They're supposed to be single pixels like the line above, but they're not. And my suspicion is that I've got two pixels overlaid on top of each other, and I've got a scan left and a scan right, which is shown up there. So I'm going to have to go and check my pixel pattern out before I release it to you guys. It doesn't make any difference,
because what we're trying to establish is the quality of the dots on those bottom two lines. And if I show you the 7mm at the bottom here and the 7.5 at the top, they're fairly similar. But if you look closely at the 7.5 ones and compare them to the 7mm ones, you'll find that the 7.5 are slightly bigger dots. Now it's only a very slight, subtle difference, but that's what you're looking for. There's only 0.5 millimeter difference in these focal distances, and that is obviously quite critical, even on a 2-inch lens, which is what we've got in here, where the focal depth is supposed to be more tolerant. This demonstrates just how critical you need to be with your settings. So we're going to settle with the 7mm, and we'll concentrate on that now, because what we've got to do is to establish the size of the dot. What, from that pattern? Yeah, well, it's not too bad, because remember I described to you that here we've got these little black dots, and they're definitely all touching. There's no dot gap, dot gap, dot gap. So if you had a dot gap, then you could say, well, I've got 0.1 dots. That was the pitch of those along the bottom line there. And we can confirm that we've actually got 0.2 dots, because remember what I said about the second pattern up. If we get a dot, a space, a dot, a space, and those dots and spaces look approximately the same, then we've got 0.2 dots.
Well, we've got two important pieces of information off that test. This is critical, knowing what the dot size is, and the second thing is to make sure you get the focus set dead right, because if you don't get the focus dead right, then you'll finish up with a dot that's even bigger than that. So what we've tried to do when we look down this pattern here is to find the smallest, crispest dots, and that tells us where the correct focus point is. Now, before we move off of our focal distance here, I will just mention again something that I nearly forgot, and that is the fact that in addition to a 2-inch lens, this machine is also supplied with a 2.5 and a 4-inch lens. Now, I would honestly suggest you do not try and use either of those lenses for this sort of work. Now, the only time you'd want to probably use something like that is if you're a little bit on the, I won't say desperate side, but there's no other solution, is if you've got an object like this that you're trying to engrave a picture onto, and it's got a curved surface, you'll need to make sure that as you scan backwards and forwards along that curved surface, you don't get too much change in the quality of the picture. And a 4-inch lens has got a much longer depth of focus on it. So, yeah, it may have a use. It will also be a much coarser picture. Now, I'm using the word coarse there, but what I really mean, there's less pixels per inch, because the dot size will be bigger. Every picture has got an inherent resolution in it if it's a bitmap or a photograph, and if you check out what that is, it will always tell you that it is pixels per inch, PPI. Now this machine, and we've already started doing it, works in millimeters. If we look over here, we've already decided that the dot size is 0.2 of a millimeter. So somewhere along the way we've got to define what resolution we can use that 0.2 dot for. So there are 25.4 millimeters in 1 inch. Okay, now these are pixels per inch. So there it is, 25.4 millimeters. Now if we divide that 25.4 by 0.2, which is the size of our pixel, our dot, we've got to make sure that our pixel is the same size as our dot. And that will give us an answer of 127 pixels per inch. So that's the resolution of the picture that we can work with. Anything more than that resolution and our dots will start to overlap. And if we overlap the dots, you remember, we're going to finish up with double burns. Here we've got a picture at 127 dots per inch. And if we draw a pattern and we've got the correct ratio of black to white, in that set of pixels. So here we've got some dots at 300 pixels per inch, and of course what happens is I've got my 0.2 dots, and what will happen is the 0.2 dots will do that, and all the gaps that you'd planned to have will disappear, and all these will overlap and double burn. So this is going to be a complete mess. So I urge you, do not mess with this number. That's what the equation says you should use. Use it. So let's go and have a look at now putting our picture into RDWorks and setting this magic number.
Okay, so there's my picture imported into RDWorks, and you'll recognise this picture as something that we have used before. I'm going to put the bitmap handle around it and just take a look at what its properties are. So at the moment it clearly tells me at the top here it's 600 pixels per inch, which is fine. Now while I'm in here I'm going to put these to 0, just put some new handles around that, and up here we can see that we've got a picture size of 101 millimeters. Now I've already put the padlock on so that the proportions remain the same, because I want the horizontal dimension to go up to A4 size, which is 297. And there we go. Now if I put the bitmap handle on again, you will see something else has happened. It was 600 pixels per inch, remember. Well, we've now changed the size of the picture, and RDWorks has actually rescaled it for us to a different resolution. Now remember, just a few moments ago we established that the best resolution that we could ever work with was 127 pixels per inch. Well, first of all, just make sure that these two are set to 0. Forget the invert. We're not going to be using a mineral material, we're going to be using an organic material. We're going to set the output resolution to what we found we had to set it to, 127 pixels per inch. Okay, so we can say apply to view, but now what we're going to do, we're going to dither the picture, and we're going to dither the picture with dot graphics. And now we should say apply to view, and there we go. We can see we've got all sorts of dots in there, and now we've got this in dot form. We can see how the picture is going to change. Now this is where you need some skill, some experience, some luck, because you've got to basically distort this picture slightly to get a good quality result onto your page. It won't come out quite like this. So what we're going to do is we're going to take the brightness up to start with, because almost certainly we shall need a brighter picture, but go up in 5% steps or thereabouts, 4.2, and apply to view. Not much difference. Let's have 10%. Well, you can see that we're bringing in some of the hairs in the background here. We're getting a bit more of the background coming forward, but it's a little bit washed out. So we need to crisp it up with contrast. So again, we'll go up in 5% steps. Apply to view. 5% step again, 10%. And maybe one more, 15%. Now this piece of software is very, very limited in its ability to play with the picture, and sometimes you need to work on this picture in a piece of external software before you bring it in. But I'm not going to do that today. We're going to stay here. We'll try and make the best of a bad job here. So let's take the brightness up again. I don't think we can get a great deal better than that. We've got quite a crisp eye there, as you can see. This eye is not bad either. So we can apply that to the view, which we've already done, and then we'll apply it to the source. We need to click on here, and there we go. So you can see that picture now tends to pop out at you. It's got more brightness in it, and we can see more of these hairs in the background. If you were going to put this picture onto acrylic or some mineral material, what you would do, you would go back into the bitmap handle. Once you're happy with the picture and you can see it on your screen looking good, you can go back in there, and you cannot any longer play with the contrast and the brightness. They're fixed. You could possibly reset the resolution if you wanted to, but we're not going to. But you do get the opportunity to go back and invert. Apply to view. And there we go. Now, there is absolutely no way that you'd be able to work on this picture in a negative form unless you've got some sort of perverted brain. So you don't actually convert to an inverted form until the very last minute. So now we've got to set the parameters. Well, we know that it's going to be a scan. We're not going to be blowing. We'll try 11% and see what happens. Now, we want nothing ticked down here at all. We're going to leave it with X swing, which means it's going to scan in both directions. And this time, the interval, we know what the interval is because we determined that when we said the dot size was 0.2 of a millimeter. So that's what we set the resolution of the picture to, 127, which is equivalent to 0.2. So we know what the interval is. The only thing that we don't know at the moment is what speed we're going to run at. And this is quite a critical factor. This is one of the secrets that I have discovered. I know from work that I've recently done that it takes 3 milliseconds or somewhere in that sort of region for a single pixel to reach its full power. Now, if you want to push the power up to 20, 30, 40, 50%, it may well take longer. But I know that when we're using dots, we're working right down at very low powers. And at low power, 3 milliseconds is an adequate amount of time to allow a single pixel to form properly. The next thing is we've already determined that our dot size is 0.2 of a millimeter. So there's 1 millimeter, and therefore we have 5 pixels in every millimeter. Now that's quite important because we're now going to take 3 milliseconds for a pixel to form times 5 pixels per millimeter, and the net result is it's going to take 15 milliseconds for a millimeter's worth of pixels. The speed of the machine is set as millimeters per second, and so therefore if we take 1 second, and 1 second is equivalent to 1,000 milliseconds, and we take that 1,000 milliseconds and we find out how many 15 millisecond intervals or how many millimeters there are, what it amounts to is 67. And so we set the speed to 67 millimeters per second. So we now go in and do that, and we set the speed to 67. That's not something we can change. Okay, so there's all the parameters set. We should now save this and go back to the machine. I've got my headset down at the bottom right hand corner, if you remember, and so we'll just set the origin there and do a frame check. Now this is going to take a long time to do, so we should come back and see it when it's done. And there we go. I think you can probably see the effectiveness of the cross flow there. You can see the smoke being drawn away. If you look very closely, you can see dots. But when we pull away, I think you'll agree that's a pretty good photo rendition. Now that's what you can expect by being careful and doing it slowly. I also think you'll see there's a significant improvement between what we were trying to do about 6 weeks ago
and that. There is no comparison. I was scrabbling around in the dark when I was doing that. That took about 40 minutes to produce that picture, and I'm sure you'll agree it's been worth it. We can see all sorts of detail on the hairs out here. We can see all these little teeny weeny hairs on his beard down here. We can even see these rings. You know, there is a huge amount of detail in there that was not evident on the original when we first looked at it. Look, we can see the sword in the background that's been pulled out. So now I'm just going to remove the 2-inch lens and replace it with a 1.5-inch lens. There's our 2-inch lens, and this was a 4-inch lens where I've taken the lens, the 4-inch lens, out of the back of the tube, and in the front of the tube here I've put an O-ring and I've modified the inside of the nozzle itself. Now that allows me to pop a smaller, this is normally a 20mm lens system. Here I've got an 18mm diameter, 1.5-inch focal length lens. Now we always put it flat side down, and on top of that I'll put a small compression tube, and by the time I screw that in there against the O-ring, it's completely solid, just very lightly clamped. Okay, so now we've got a 1.5-inch lens in here. But I stress again, this is not something that's standard and available from Thinklaser. This is something that I've designed and made myself. We're going to use the same paper, but we've got to go through exactly the same exercise because we've changed the focal length and we don't know what size the dot is that we're going to produce, and we don't know exactly what the focal length is, so we need to prove it. While we're here at the moment, what I want to do is just point out to you the fact that I have got a mild steel plate sitting on top of the bars, and this mild steel sheet is approximately level with the frame of the bed. There's a good reason why I like using this steel plate. First of all, as you can see, I can put magnets on it. Secondly, it does not allow the air to pass down through it. It blocks off the air that would normally pass through either the bars or the honeycomb table that you have on the top here. And in this particular instance, what will happen is the air passes across the top of the table like this to those holes at the back there. Now that produces a cross flow, which is absolutely essential, in my opinion, when you are engraving, because you don't want the air to go, ugh. I mean, let's face it, if this is the size of the picture and that's the size of the open area around it, there's more open area than there is picture. So what will happen is you'll get most of your air just disappearing straight down there, and it'll have no cleaning or purging effects on the top surface of this this graphic that we're going to work with. So I always make sure that I get a cross flow, a very high speed cross flow, to pull the fumes backwards. And the other thing that I do, and I mentioned it before, is that we set the graphic start point down here, so that when we engrave, we should be engraving backwards and forwards like this and gradually moving towards the back of the machine. And that means that all the smoke that's generated during the engraving process is being pulled backwards. Now, it tends to come up in the air before it goes backwards, so very little of it is ever going to reach this clean paper here. But just in case it does, by going backwards, it means that we're going to not get any of that debris painting our picture. We're going to leave the picture that we're producing in a nice, clean, smoke-free environment. Now, this steel plate is not something that is standard on the Thinklaser machine. You're going to have to make this for yourself. Don't get any plated material, just plain, raw, mild steel. If it goes a little bit rusty or a little bit messy, picking up fumes and condensation, particularly if you're doing MDF, you can get horrible brown, mucky stuff on the surface there. Some acetone will clean it off, and if it goes rusty, then all you need is an industrial cleaning pad. And this abrasive pad will keep your table nice and clean. So we think this is 7.5 mil. So what I'm going to do, I'm going to start at 8.5
and we'll work our way from a millimetre above and a millimetre below the ideal setting point. Now I will inspect these and then we can look at them under the microscope. There's better separation between the 7 than there is between the 7.5. So in fact I'm going to award that one the prize, 7mm. And now we're going to estimate the dot size. Now this is going to be interesting. That's my estimate for that one, 0.15. So they're slightly smaller, which means we've got to go back and we've got to revise the picture, because we've got to reset the pixels per inch. We could run the same picture, but I don't want to do that because the rules are the rules. So I've redrawn the picture so that it's got an interval of 0.15 and a resolution of 170 pixels per inch. Now what we've got to do is calculate the speed, which I can modify here on the machine. The key thing is 3 milliseconds is the time that we're working with for a single dot. This time we've got 1 millimetre, and in 1 millimetre we're going to divide that by 0.15, and that equals 6.7 pixels per millimetre. We've got this magic number of 3 milliseconds that applies regardless of the number of pixels per inch. That's just a fixed constant. Consequently, we're going to have to multiply the 3 milliseconds by the number of pixels per millimetre. So that tells us it's going to take 20 milliseconds to do a millimetre's worth of pixels. Remember, our speed is millimetres per second. So in 1 second we have 1,000 milliseconds, and we can divide that by 1,000 milliseconds by 20. That's going to generate a speed of 50 millimetres a second. Higher resolution, lower speed. So we've now got to set the speed to 50 millimetres a second. And because we've reduced the speed, the chances are that we shall probably have to reduce the power as well. At the moment the power is set to 12%. So now we've got to go back to our test pattern again. Now I'm sure it's pretty obvious to you that 10% is so much lighter than 11%. There's a huge difference there between those two. But there isn't a huge difference between 11, 12 and 13 in terms of colour. But there probably is in terms of depth of pixel. So what we've got to do now is very carefully look to see whether or not we're going to use 11 or 12. Now that's one of the reasons why when we look at this pattern you'll see there's a load of bars across the top. They are multiple pixels and they will help us to decide whether or not we should choose 11 or 12. Is 12 burning too deep relative to a single pixel, or is 11 a more balanced view between one pixel and a group of pixels? And that's an assessment that we've got to try and make. Well, I think I'm going to settle on 12%, because 13% the dots are getting just a little bit bigger. The colour difference is not huge, so I think we'll settle on 12%. So 12% and 50 millimetres a second, those are the settings. We were very pleased with the quality of picture produced by the 2-inch lens. But let me show you what happens with a 1.5-inch lens. It's quite staggering, I have to say. I did not think it would be as big a difference as that. Now, part of the advantage of this is the fact it's got a deeper colour to it. And when you think about it, the reason for the deeper colour is because although I've reduced the power very slightly, the energy density in the lens is twice as much as it is in this lens. So I've got a much sharper hit. But look at the clarity of some of this stuff down here. This is the same picture, by the way. I haven't messed with the tonal range of the picture. It's exactly the same picture as this one. The only difference is the fact that it's done with a 2-inch lens, and probably the colour difference between the two is because we've got a higher power density in each one of these dots. Okay, so I was slightly wrong again. There is a big difference between a 1.5 inch and a 2-inch lens. But the whole purpose of today's project was to demonstrate that there is a formula that you can follow to get a good quality photo engraving. I'm extremely pleased at the results we got today. The 2-inch lens was exactly what I expected it to be. It was a good quality rendition of the original. But when we compare it to the 1.5-inch lens, where we get a really good deep contrasty picture because we're able to get a much deeper burn, it does show you the value of having the right material in the background and the right concentration of energy. I think we've got much higher energy densities here that's able to produce this burn without actually etching away the material. If you start overlapping your dots, you get a 3D feel to your picture, and there are no 3D feels to either of these pictures. So I know that my dot quality is good. These are exactly the same picture. These are exactly the same cards. These are done, as it happens, at exactly the same power. This one was done at 12%, this one was done at 12%. I think this one was done at 67 millimeters a second, and this one was done at 50 millimeters a second. This is lower energy density and faster, which maybe accounts for why it's slightly more washed out. Now, I'm not trying to put Thinklaser into a tight corner or anything like that, but I think that you can see from these results that the difference between a 2-inch lens and a 1.5-inch lens, which is not available as standard, is quite staggeringly different. Now, without anything to compare it with, this is still quite a nice photograph. But this one here is something a bit special. This is almost a perfect sepia photograph. So we've succeeded in our aim. There is a formula which will guarantee that you get almost the perfect photo engraving. I think in a future session we ought to take this a little bit further and go into mineral materials such as glass, slate, and maybe into plastics like acrylic, which are things that people tend to use a lot of. So whether we use the same picture, which might be a good comparison to see just how we get on with this picture in different materials, we'll have to see. But thank you very much for your time today, and I'll see you in the next session.